In this lesson, we are going to learn how to determine the empirical formula of a compound containing carbon, hydrogen, and other elements. So here are the steps. The first step is, of course, to determine the mass of each element from the given data. So the goal is to figure out the mass of each element. And once you have your masses, you can convert the masses to mole. Because the empirical formula is about finding the moles ratios relative to the lowest number of moles. So of course for step 3 is divide all the moles by the lowest number of moles to get that ratios of moles of the empirical formula. Let's do an example problem together. Here I have a pure substance contains carbon, hydrogen, nitrogen, and oxygen. When a 1.24 grams of the substance is analyzed, the following data were found. We have a 2.24 grams increase in the mass of carbon dioxide absorber. And remember, the combustion analysis is about finding what is being absorbed, either water or oxygen. And the changes in the absorber, in this case carbon dioxide, is how much mass of carbon dioxide is being produced. And that allows us to convert from carbon dioxide being produced to the mass of carbon in the substance. Then we also find out the sample contained in terms of 0.0650 grams of hydrogen. Notice it's not given to us in water, so this makes our life a lot easier. Then we have 28.8% is nitrogen by mass. And of course, if we have percentage, we can always find the mass by take the percentage times the total. So let's look at the problem. First of all, we need to be organized. So basically, we look at the list of elements and we organize them in terms of a list. So what I have here is carbon, hydrogen, nitrogen, and oxygen. They're in the order of given to us, which will be the order of the chemical formula as well. So what we have here, of course, is based on our information. Let's look at the data of number 1. We have a 2.24 grams increase in the mass of carbon dioxide absorber. That tells you that how much carbon dioxide is being produced. So of course we can solve for the mass of carbon, which I wrote right here. This is our answer. So this is supposed to be hidden from you, okay? So what we have here is 2.24 grams of carbon dioxide time, based on the stoichiometry flowchart, time the molar mass conversion factor of carbon dioxide, which the grams on the bottom. So it's going to cancel out and give us moles of carbon dioxide, and we're going to convert to carbon, which is multiplied by the mole ratio. In this case, is 1 moles of carbon dioxide relative to 1 moles of carbon, and the moles of carbon dioxide cancel out. Now we convert that carbon to mass, which times the molar mass conversion factor of carbon, 12.01 grams on top, and the moles on the bottom to cancel out, give us 0.611 grams of carbon. But I'm not going to write it down because I need the space to convert back to moles and so on. That's going back to step 2. And if we look at data number 2, it's giving us the mass of hydrogen, so we just write it down here. We don't just solve for it. Now we look at the data of number 3, 28.8% is nitrogen by mass. Now look at the term mass. Our mass in total is 1.24 grams. So what we can do is look at number 3, and we take that percentage time the total, because percentage of a total is basically a total right there, means time. But before that, convert this percent to decimal, and we time that, and we get ourselves the number of grams of nitrogen in the sample, 0.357. So that's what we have here. And lastly, we don't have any data about the oxygen, but oxygen is the only element left in the list. So of course we can solve this by easily taking the total minus the sum of all the parts. What are the parts? The parts are basically the grams of carbon plus the grams of hydrogen and the grams of nitrogen. And the leftover in this case is oxygen. So once we do that, we are going to get our answer. And here we have, to solve for grams of oxygen, we take the total, which is 1.24 minus the sum of all the parts, which is the mass of carbon, hydrogen, and nitrogen, and give us a mass of oxygen. So our mass of oxygen is equal to 0.207 grams. Now, let's go back to step 2. Let's convert this to mole, because we need to look at moles in order to determine the empirical formula. So let's go back to look at carbon, and of course we could multiply by the conversion factor of molar mass. In this case, carbon is 12.01 grams of carbon, and that is equal to 1 moles of carbon. And we plug this into the calculator, we would have 0.0509. And for hydrogen, we do the same thing. 1.01 grams of hydrogen, 1 moles of hydrogen on top of the gram cancel out, and that will give us 0.0644. Then we do the same thing to nitrogen, times by the molar mass conversion factor of nitrogen, which is 14.00 grams of N, and 1 moles of N on top, gram of N cancel out, which is right here. So we have 0.0255 moles of nitrogen. And lastly, we have for oxygen, which is over 16.00 grams of O, 1 moles of oxygen, and that will give us, of course the grams of O cancel out right here, and this gives us 0.0129 moles. And if we look at all the values, this is our smallest number of moles, so we divide by this number of moles. And of course that gives us 1. That's going back to step 3, just like solving for the empirical formula. Now let's go back to over here, we divide by that same number and give us 1.97, and we can round that to 2 easily. So that tells you that this chemical formula has 2 moles of nitrogen. And we do the same thing for the hydrogen, divided by the lowest number of mole, which is 0.129, and this gives us 4.99, and we can round that to 5. And lastly, we have carbon, again divided by the lowest number of mole, which is 0.0129, and this gives us 3.94, and we can round it up to 4. So in the end, what we have here is an empirical formula, which contains 4 moles of carbon, 5 moles of hydrogen, 2 moles of nitrogen, and 1 mole of oxygen. So basically we have C4H5N2O, and that would be our empirical formula for this compound.